ADF4110 is a 16-pin SMD phase lock loop with programmable dual modulus. The chip is very similar and pin compatible to the LMX2306 except the latter has a fixed modulus of 8. PIC 16F84A interfaces the 4110 whose external components are minimum and straightforward. BC547 is used to generate reference frequency at 10 MHz and the BF961 is used to generate VCO around 144 MHz. The PIC will write 4 types of 24-bit information called IFR and N to the phase lock loop. I stands for information, F for function, R for reference, and N for VCO divider. IFR contain general information and are written only once at startup. N is written whenever there is a change in VCO frequency. The IFR are not very difficult to understand, however, the N is a bit confusing compared to MC145-170. In the MC145-170, two specific numbers X and Y are used to divide the reference and the VCO. In this example, X is 100 to set step size 100 kHz and Y is 350 to divide the VCO down from 35 MHz to the same 100 kHz for comparison. At 35 MHz, the frequency is not high enough to create a problem. But when VCO frequency increases to, say, 2.4 GHz, the value of Y is becoming too large to fit in the allowable register space. That said, let's assume for a minute that we want to generate 2.4028 GHz. A new method for calculating the value of Y is introduced. This method is called fractional N. The fractional N is basically the product of A and B plus C as shown here, with N equals 64, A equals 375, and C equals 28. The result becomes 24028. By multiplying the result with the step size 100 kHz, the final result is exactly equal to the VCO frequency that we want to generate. To simplify this method, a specific formula that defines the relationship between VCO frequency 64, 375, and 28 is created. The 64 and P comes from the use of modulus 64. The 375 or B comes from an arbitrary number, and the 28 or A comes from selecting a specific number between 0 and 63. The P or modulus of 64 is sometimes called 64/65. In modulus of 64, the value of A can be anything from 0 to 63, no more, no less. In other words, A is the fractional portion of 64 modulo, which implies further that whenever A exceeds 63, it will be reset to 0, at which time the value of B increases by 1. In ADF4110, modulus is software selectable to be 8, 16, 32, or 64. This implies that in modulus 8, the value of A can be anything from 0 to 7, which also implies that in modulus 16, the value of A can be anything from 0 to 15. And in modulus 32, the value of A can be anything from 0 to 31. ADF4110 allows the B to contain 13 bits and has maximum value of 8191. Similarly, the allowable length of A is 6 bits, so it has maximum value of 63, just enough to do the modulus of 64. The B is called B counter and the A counter, sometimes called swallow counter. This slide shows example VCO frequency around 27 MHz using modulus of 8, implying the value of A to be anything from 0 to 7. When A exceeds 7, it resets to 0 and B increases by 1. Similarly, with modulus of 16, where A swings in the range of 0 to 15, and with modulus of 32, where A swings in the range of 0 to 31. We will proceed with building a prototype in which the VCO is locked to 142.00 and 143.95 MHz using modulus of 8. At 142 MHz, the value of B is 1775 and A is 0. At 143.95 MHz, B is 1799 and A is 3. This shows bit pattern that will be written for I, for F, for R at 10 kHz step size, and for N at 142 MHz. As mentioned earlier, the VCO is built around the BF961, which has super high gate impedance and can operate with high stability up to 200 MHz. The VCO is shielded and attached to the phase lock loop circuitry. This is the close-up of the phase lock loop, connecting to a frequency meter. Actual readings are a bit too high. We can adjust the crystal loading capacitor to bring the reference frequency down. But just to check the software functionality, this is good enough for the ugly prototype. And finally, the PIC source code for reference.